In this video, we are going to show how to find two complex numbers with a given sum and with given moduli. So, for the two unknown numbers, their sum is known, and their moduli or absolute values are known. Let's start by writing the problem statement. In this problem, we would like to find two complex numbers z1 and z2, such as the sum of the two complex numbers is known. z1 plus z2 is equal to a known complex number u. Also, the moduli or absolute values of the two complex numbers are known. The modulus of z1 is equal to a known real positive number r1. And the modulus of z2 is equal to r2, which is also a real positive number. So, in this video, we are going to solve the complex number equation, z1 plus z2 equals u, such as the modulus of z1 is equal to r1, a given positive real number, and modulus of z2 is equal to r2, a known positive real number. To solve this equation, we are going to use the polar representation of complex numbers, instead of algebraic representation, or the rectangular coordinate form. More precisely, z1 is written as r1 times exponential of I times theta 1, where r1 is the modulus of z1 and theta 1 is the argument of z1. As z1 is unknown and r1 is given, the argument theta 1 is here unknown. Likewise, z2 is written as r2 times exponential of I times theta 2, where r2 is the modulus of z2 and theta 2 is the argument of z2. Here also z2 is unknown and r2 is given. So, the argument theta 2 is unknown. Also, the complex number u is written as a times exponential of I times alpha, where a is the modulus of u and alpha is the argument of u. As the complex number u is given, its modulus, a, and its argument alpha are both known. To close this first part of problem presentation, we are going to use polar representation of complex numbers. z1 is equal to r1 times exponential of I times theta 1, z2 is equal to r2 times exponential of I times theta 2. And u is equal to a times exponential of I times alpha. The problem that we are going to solve writes, z1 plus z2 equals u. We are going to substitute z1, z2, and u, by their polar representations. Thus, the equation writes now, r1 exponential I theta 1 plus r2 exponential I theta 2 is equal to, a, exponential I alpha. For this equation, we have four parameters, 3 moduli and 1 argument. r1, r2, and a are the absolute values of z1, z2, and u. And alpha is the argument or the phase of u. In this equation, we have two unknowns, theta 1 and theta 2, which are the arguments of z1 and z2, respectively. The advantage of using the polar representation here is to have two, and only two unknowns, that are real numbers. Recall that complex numbers are two-dimensional. Thus, one complex number equation is equivalent to two scalar equations. Hence, the problem we are going to solve is equivalent to a problem of two scalar equations of two unknowns. Let's show first some applications. Later we are going to describe the solution of the previous equation. The previous complex number equation has multiple applications in geometry and its solutions are useful in engineering such as machine kinematics and design, or light refraction. For example, if two given points A and B are such as their relative position is known. So we know, how far is B from A? Let A be that distance. Also using a reference ij, we know in which direction B stands compared to A. The 2 points define a vector AB of known magnitude and angle. The magnitude of the vector AB is known and it is equal to the distance AB. The angle is also known. Let alpha be that angle. The angle is always defined starting from the positive horizontal axis, axis I. The vector AB can also be assimilated to a known, complex number u. Thus, the modulus of the complex number, a, is equal to the distance AB. And, the argument, or phase, of the complex number is equal to the angle of the vector. And, we would like to join the 2 points A, B, using two vectors, z1 and z2. However, the magnitudes of the two vectors are known magnitudes, r1 and r2. On the opposite, the directions or the angles of the vectors are to be determined. It is typically the problem of joining 2 points, using 2 sticks, or 2 bars, of given lengths. In that cases, we need to play with the direction or angles of the sticks, to be able to do it. A second geometrical applications is to find the intersections, between two circles, having centers A and B, known, and having radii, r1, and r2, also known. Before starting the derivation of the equation's solution, we need first to recall some concepts related to complex numbers. To solve our complex number equation, we need to recall some basics of the complex number theory. First, we need to work with the conjugates. Mainly, the conjugate of a complex number is the complex number that has the same real part, but it has the opposite imaginary part. Using polar representation, the conjugate has the same modulus as the original complex number. However, it has the opposite phase. If a complex number z has a module r and an argument theta, its conjugate is denoted z bar, and has the same modulus r, but its phase or argument is equal to minus theta. If the complex number z is multiplied by its conjugate z bar, the square of the modulus is obtained. Thus, z times z bar is equal to r square. Also, we need here the expression of the cosine obtained from Euler formula, that is cosine theta is equal to half the sum of exponential of I theta and exponential of minus I theta. After presenting some useful applications, and after recalling some basics of complex theory, we are ready now to derive the solution of the complex equation. The complex equation writes, z1 plus z2 is equal to u. First, we are going to move z1 to the right side. So, we have z2 is equal to u minus z1. Now, if an equation is true, the complex conjugate of the equation is still true. So, if z2 is equal to u minus z1, then the conjugate of z2 is equal to the conjugate of u minus z1. Or, z2 bar is equal to u bar minus z1 bar. At this step, I have, in one hand, z2 is equal to u minus z1, and, in another hand, I have z2 bar is equal to u bar minus z1 bar. I can then multiply the two equations. Hence, I will have at the left side z2 times z2 bar equal to u minus z1, which is the right side of the first equation, times u bar minus z1 bar, the right side of the second equation. In the previous slide, we have started with the equation z1 plus z2 is equal to u. And, we succeeded to derive that z2 times z2 bar is equal to u minus z1, times u bar minus z1 bar. Recall that for any complex number z, z times z bar, is equal to r square, the modulus square. This rule is true for z2, thus z2 times z2 bar is equal to the modulus r2 square. And we can substitute this in the left side of our equation. Thus, at the left side we have now r2 square, the modulus of z2 square. This is a major step in solving the complex equation as we have succeeded to remove z2. Instead, we have its modulus r2, which is known. Hence, the equation is expressed in terms of only z1 and its conjugate. Now, we can take care of right hand of the equation. Mainly, we can develop the multiplication of the two brackets. So we will have u times u bar plus z1 times z1 bar, minus u times z1 bar, minus z1 times u bar. In this last form, we have u times u bar, which is equal, a square, a is the modulus of u. Also, z1 times z1 bar, is equal to r1 square. Substituting z1 times z1 bar equals r1 square, and u times u bar equals a square, in the right side of the equation, gives r2 square is equal to a square plus r1 square minus u times z1 bar minus z1 times u bar. Starting from the equation z1 plus z2 is equal to u, we have established the equation r2 square is equal to a square plus r1 square minus u times z1 bar minus z1 times u bar. In this equation, r2, a, and r1 are the moduli of z2, u, and z1, respectively. To move forward, we are going first to move the completely known terms to right, mainly r2 square. Also we are going to move the terms with unknowns to the left side. Thus, the equation now reads, u times z1 bar plus z1 times u bar is equal to a square plus r1 square minus r2 square. To be able to calculate the left side of the equation, we need the polar representation of z1 and u, which are u is equal to a exponential of I times alpha, and z1 is equal to r1 exponential of I theta 1. Next, we substitute the polar representation of u and z1 into the left side of the equation. Mainly, we substitute to u, a exponential of I alpha. We substitute to z1 bar, r1 exponential of minus I theta 1. We substitute to z1, r1 exponential of I theta 1. And we substitute to u bar, a exponential of minus I alpha. The first term of the left side simplifies to r1 times a times exponential of I times alpha minus theta 1. And the second term of the left side simplifies to r1 times a times exponential of I times theta 1 minus alpha, which is also equal to r1 times a times exponential of minus I times alpha minus theta 1. Considering this, the left hand of the equation reads r1 times a times exponential of I times alpha minus theta 1 plus r1 times a times exponential of minus I times alpha minus theta 1. Dividing the equation by r1 times a gives, at the left side, exponential of I times alpha minus theta 1 plus exponential of minus I times alpha minus theta 1, and, at the right side, a square plus r1 square minus r2 square divided by r1, a. Having this last equation, and to be able to move forward, we need to use the cosine expression in terms of the argument, which writes cosine theta is equal to exponential of I theta plus exponential of minus I theta, divided by 2. Considering this formula, the left side is equal to twice cosine of alpha minus theta 1. Hence, twice cosine of alpha minus theta 1 is equal to a square plus r1 square minus r2 square, divided by r1, a. Then, alpha minus theta 1 is equal to plus or minus r cosine of a square plus r1 square minus r2 square, divided by 2 r1, a. Plus or minus here used, because cosine of angle is identical to the cosine of the opposite of the same angle. Finally, theta 1 is equal to alpha, minus or plus, r cosine of a square plus r1 square minus r2 square, divided by 2r1, a. We have started from the equation z1 plus z2 is equal to u. Using the polar representation of the z1, z2, and u, we have derived that theta 1, the argument of z1, is equal to alpha, the argument of u, plus or minus r cosine of a square, the modulus of u square, plus r1 square, the modulus of z1 square, minus r2 square, the modulus of z2 square, divided by 2 times r1 times a. The cosine of angle ranges between -1 and 1. Thus, the r cosine function cannot take values lower than -1 and higher than 1. So if the fraction inside the brackets is higher than -1 and lower than 1, there is 2 possible values of theta 1. If the fraction inside the brackets is either equal to 1, or equal to -1, there is only one value of theta 1. And, if the fraction inside the brackets is either lower than -1, or higher than 1, there is no real value of theta 1. Using the same approach and the same steps, we can also show that theta 2, the argument of z2, is equal to alpha, plus or minus r cosine of a square plus r2 square minus r1 square, divided by 2 times r2 times a. As for theta 1, the expression obtained for theta 2 can give either 2 possible values, or 1 possible value, or no possible real value. There can be up to 2 possible solutions for theta 1 and theta 2. What we have showed here is that if z1 and z2 equal to u, then theta 1 and theta 2 should have the expressions in terms of r cosine, shown here. However, the opposite is not necessarily true. If the arguments theta 1 and theta 2 have the expressions shown here, then z1 and z2 are not necessary solutions of our complex equation. So after calculating theta 1 and theta 2, using the expressions involving r cosine, shown here, we need to check that the corresponding z1 and z2 are really solutions of the complex equation. Now, we are going to present the solution of the complex equation. If one of the two previous fractions inside the brackets is either strictly higher than 1, or strictly lower than -1. If only one of the 4 inequalities here is true, then the complex equation has no solution. If the two fractions range between -1 and 1, there can be up to 2 possible values for theta 1. One solution using plus and one value using minus. Similarly, there is up to 2 possible values for theta 2. One solution using plus and one value using minus. There is 4 possible combinations. We can first use plus for theta 1 and plus for theta 2. We can also use minus for both angles. We can use plus for theta 1 and minus for theta 2. And, the last combination, is to use minus for theta 1, and plus for theta 2. In all, there are 4 possible combinations, but there are at maximum 2 solutions. 2 circles intersect, in 1 point, and at most 2 points. Here also there is one solution, or at most 2 solutions for the complex equation. Thus, we have to check which 1 or 2 combinations of the 4 combinations are really solutions of the complex equation. Let's apply these results to an example. Let's consider the following example. We would like to find two complex numbers z1 and z2 such as, their sum is equal to complex number, 3 times exponential of I times, pi over 4, and such as, the modulus of z1 is equal to 3, and the modulus of z2 is equal to 5. In this case, we have r1 is equal to 3, r2 is equal to 5, a is equal to 3, and alpha is equal to pi over 4. First we start by calculating the fractions inside the r cosines to check if they are in the good range for the r cosine function. Substituting the numerical values of r1, r2, a, and alpha, into the two fractions, we obtained -7 over 18 for the first fraction, and 5 over 6, for the second fraction. Thus, the two fractions are higher than -1, and lower than 1. We will be able then to use the r cosine function. The r cosine of the first fraction is equal to 1.9702. And the r cosine of the second function is equal to 0.5857. Thus θ1 is either equal to 2.7556, or -1.1848. And θ2 is either equal to 1.3711, or 0.1997. To our original complex equation, there is 4 possible solutions that are listed. After substituting each combination in the original solution, it comes that only 2 are really solutions of the complex equation. Finally, the solution of the complex equation are either z1 equal to 3 times exponential of 2.7556i, and z2 is equal to 5 times exponential of 0.1997i. Or the second solution, z1 equal to 3 times exponential of -1.1848i, and z2 is equal to 5 times exponential of -1.3711i. Thanks for watching.